Hello, my name is Jan, and in this video I will show you my project on the topic of epileptic seizure classification based on a deep learning algorithm and its integration on a system on chip. In the first part of the video I will talk about the algorithm and the methodology that was applied to train it and to make it ready for hardware integration, and in the second part of the video I will show you the system that involves the DE10-nano board and the Cyclone 5 system on chip. Before presenting the algorithm and the system, I would like to briefly describe epilepsy. Epilepsy is a neurological disorder that is marked by abnormal electrical discharges in the brain, and typically symptoms occur such as loss of consciousness or involuntary movement. Nowadays, it is estimated that 65 million of people worldwide have this disease, but most importantly, for 30% of them there is no available treatment that is fully effective. And this creates the need to develop new treatments. Although various methods have been proposed in the past for seizure detection and prediction, one of the main objectives in this project is to explore deep learning and evaluate a particular architecture of a deep neural network with a recurrent data dependency inside it. The neural network starts with a 2D convolutional layer with a rectified linear unit as activation function, followed by a 2 maximum pooling layer to reduce the amount of data, and the data is also flattened to prepare for the GRU layer. The GRU layer is composed of several units that work in parallel. Each one of them have a memory cell called S, which is passed to the next layer at the last iteration of the sequence. The H function is calculated using new input data and data from the previous state of the cell S to calculate its new state. The R gate determines the fraction of the S cell that is used for the calculation of the function H, while the Z gate determines how much of the H function will modify the new state of the cell. The output layer is a fully connected layer with a softmax activation function that separates the different classes in a probabilistic way. For epileptic seizure classification, we are interested in 3 different classes, being the interictal class corresponding to a healthy condition of the patient, a pre-ictal period occurring right before an onset, and an ictal class which corresponds to the seizure itself. The data is fetched from a public database with the EEG recordings of pediatric patients diagnosed with epilepsy. And these recordings were sampled at 256 Hz with 23 channels in parallel. Firstly, some pre-processing steps are applied to the data. After the parsing of the EEG recording files and the summary files containing the start and stop times of seizures, the data is undersampled, labeled according to the corresponding classes, and finally standardized statistically using mean and standard deviation. The sequences are also cut into batches of time steps to prepare for the training algorithm. The training is performed using the truncated backpropagation through time algorithm, which is an optimized version of a simple backpropagation through time, which is the main algorithm for the training of recurrent neural networks. The third step in the procedure is the retraining. It consists of training a quantized low-precision version of the full-precision algorithm trained in the previous step. The objective is to reduce the memory footprint of the neural network, as well as the cost of the computations in the forward pass equations in view of hardware integration. It is very similar to the training phase, except that the initial values of the weights are set to the solution found for the full precision algorithm. After the retraining, the system is ready for the inference phase, consisting of the processing of new unlabeled data through the forward pass equations only, which generate predictions regarding the class of the sequence being analyzed. The test phase is implemented using the DE10-nano board, while the pre-processing, training, and retraining steps are all realized in higher-level software code using Python. Let's now focus on the actual system handling the test phase. The system is composed of 3 main parts, including a PC, the HPS of the DE10-nano board, and an accelerator on the FPGA. The PC is used for the storage of the database to avoid large onboard memory usage. The HPS handles the communication between the PC and the accelerator and synchronizes between them. The 2 C applications communicate together through TCP/IP protocol. The PC has a server and the HPS has a client. The client triggers the server for a new chunk of data, parses the data it receives, and transfers it to the accelerator before starting it and sending a new trigger to the PC until the entire dataset has been covered. Let's now look at the inner architecture of the accelerator and how it interfaces with the Avalon bus. The accelerator has 4 slave components for both control data and data transfers. The routing of the on-chip memory to the classifier and the Avalon bus is realized in an intermediary component called the RAM wrapper. The classifier itself contains arithmetic blocks including multiply and accumulate units for the matrix vector products calculation, which is one of the most common operations in deep learning. It also contains the quantization and activation units, realizing those two functions depending on control signals. There is also an array of double comparator units for the maximum pooling layer. There are several control blocks inside the classifier, controlling the arithmetic units in turns depending on which layer is being processed. In fact, the arithmetic units, especially the multiply and accumulate units, are fully or almost fully used at a given time inside one layer. And due to the data dependencies as well, the layers must be treated sequentially. The memory components are displayed in blue. While most of the data is stored in on-chip RAMs, including the parameters and the input batches, some extra memory is used to keep temporary results, especially in the data flow for the GRU layer. A FIFO is also used as a buffer to reorganize data previously stored in the on-chip RAM after the max pooling layer and corresponds to the flattening layer in the network's architecture. Having a very few number of parameters, the output layer is independent of the rest of the architecture and has its own arithmetic units and control blocks. It operates in a very similar way as the other layers, except for the softmax activation, which has its dedicated block containing a lookup table for the exponential function coupled to a divide and accumulate component. Unfortunately, I cannot explain all my design choices or present the accelerator's components with much detail in this video, but let's focus on a specific part, being the GRU layer. The control block of this layer contains a main finite state machine that sequentially follows the equations describing the GRU unit. This finite state machine is broken down into four main stages. The first three compute the Z, R, and H functions, and take up the majority of the time spent in the layer because they realize matrix vector products for matrices with a relatively large size. The fourth part implements the last equation of the GRU unit and consists of element-wise operations between intermediary result matrices Z and H. Also, you might have noticed the red states in the finite state machine, and they correspond to break cycles during which the arithmetic pipeline is stalled to wait upon a required result for the next calculations to be available. The typical data flow inside the GRU layer is a pipeline that starts with data fetching from the memory sources, which for a direct matrix vector product is the FIFO and the WOC-RAM for the weight. The MAC units then receive the data and calculate partial products in parallel such that the entire array is fully busy, and once the results are available, they are quantized and stored into temporary registers. So that was it for the presentation of the system, and I will now leave you with the footage of the demonstration, which has been accelerated to fit in this video, and hopefully the indications on screen will help you follow me through the process.